Hey everyone, welcome to my channel. What I wanted to do today is share with you a project that I've been working on, sort of a learning project that it's been taking a while for me to get up and running with it. It's been a little bit intimidating to get started with just because of the nature of the subject. But what I wanted to start on, and what I've always wanted to do with computers, is develop some type of artificial intelligence that can go and experiment in a space, like a game, and play it and learn how to beat it and see what challenges come up. So what I wanted to share with you guys is my progress so far in trying to get a reinforcement learning model trained so that it can play Breakout, which is a 1978 Atari game that was created by Steve Wozniak back in the 70s. It's been iterated on a number of times, sort of copied, but this is the original one. And it's one of the baseline environments that come with the systems that you can get up and running with. And instead of playing Pong, or instead of playing the common game, which is called cart pull, that's a game where you have a cart in the center of your screen and it tries to hold up a stick that starts off angled. The cart needs to balance. That's the startup game, but I've always been interested in, I grew up playing video games, and I've always been interested in figuring out how artificial intelligence would work in order to, can it solve these games? Can it win at them? So in deciding to work with Breakout, I was kind of interested in it because there was a little bit of research that was done on the game, and there are some benchmarks that have been established already, one by DeepMind and another, and it's been beaten a number of times in the past couple of years. But they were able to, it has like a sort of baseline that you can measure up the model that you've built with. It has some articles around it that I can read, and it has some scientific papers that were written on it. All of these things make it a little bit easier to understand, where you begin. If I started with, some kind of obscure, not so obscure, but not super popular, like Super Nintendo game or something like that, I wouldn't be able to tell if I was making the right choices and I was doing the right things when trying to train these models and develop, a system of feedback for the reinforcement learning loop. So, what is artificial intelligence? What is reinforcement learning in this context? Artificial intelligence, it's a very broad term. It can be used, it's kind of like defining art. It can be almost anything that is a computerized system that handles some type of logic, you could argue, is artificial intelligence. In this area, I'm talking about the systems built with machine learning. So when you look at this space, there are typically three areas that you can kind of break everything down into, which is supervised learning, and this is all on a high level. Supervised learning, you'll have a series of items that you can identify. So maybe pictures of cats, pictures of dogs, they're cats and dogs. You train a model based on how well it's able to predict and then iterate over that to try to get at some type of decision boundary. And then there's unsupervised learning, which again on a high level kind of looks at unlabeled data and tries to find clusters of similar information inside that data. So that's a slightly different use case than supervised learning. Those two make up a large part of a lot of the artificial intelligence that we see currently out today, and what we've become familiar with using and talking about in the tech world. But reinforcement learning is still in its sort of emergent state, and that's kind of clear by, as I found out working with some of the libraries and some of the documentation there, which I'll get into in a minute. But the third area is reinforcement learning, which takes a completely different approach. You have an environment, and that can be any type of environment that you can write a programmatic system for. In our case, it would be the full screen of the Atari system. In the cart pull game that I described with the cart that moves back and forth trying to hold up a pole, they've actually coded it so that you can get the actual X and Y coordinates of the cart. So you don't have to try to work with the entire screen. You can get a more fine piece of data to work with. And in that environment, you have some type of computerized agent that takes actions and an interpreter that interprets the reward as defined in the environment for taking those actions. And what you want to do is maximize the reward for each step as you iterate over and over and over. And it's interesting to me because it is on a high level. I don't want to, make any unqualified opinions about how it relates to psychology, but in a loose way, we can kind of understand that as we work with, as we encounter things that we're unfamiliar with, we iterate over doing the same thing or a similar thing and change our behavior based on how successful we were in doing something. So it loosely relates to how, we learn as humans, and that's where back in the 70s when it was being developed, 50s, when some of the first theories were coming out, and that's where some of the first theories are coming out with supervised and unsupervised learning as well. This one tried to look at how animals or humans learned and sort of try to replicate that in a mathematical way. We're now getting to the place where we have the compute power in order to do that, but it's still in the early nascent stages of any AI based on machine learning, but very specifically in reinforcement learning, there have been some applications, but because of the vast, compute power required to arrive at highly performant models for complex environments, it's still in the early stages, and there's a lot of papers that come out frequently. Some of the papers that were breakthrough in 2015 are now completely obsolete, and the area is growing, and it's just something that I find myself interested in. So I decided to try to film a couple, decided to go down this path, see where I end up. I'm by no means an expert at it right now. Maybe I'll get to an expert level. I'm really just taking the libraries that are available, seeing if I can play around with them. I'm doing my own textbook learning, my own video-based learning, online learning, trying to read the papers themselves, because that's sometimes where the information actually is, and seeing if I can iterate and get better and better at this. So we're starting with Atari, and Atari games are nice because they're actually integrated into one of the common libraries, OpenAI. It's already integrated so that you can quickly spin it up and get working with it, It is a sort of limited space where you have usually you can only move left or right. Maybe you have up and down, and you have a fire button. It's not like Super Nintendo or more modern games where there's a number of different controls. You have like 10 different buttons. Some of them are not just buttons, but they're triggers with sort of continual settings. Every new console now has a left and right trigger where you can pull down at a certain rate, and it gives you a different response based on how far you've pulled the trigger. Those are sort of more difficult to model. If you look at the what was available in the 1970s, it was kind of like left, right, up, down, and fire button, just a fire button. So the scope of that action space is limited, and that can help us out in being able to build a model and get, at least, when you get started, it's going to help you focus on what you need to learn in order to get to those more complex games. So I'm starting with Atari, and one of the games, I don't know why, I just remember it from being a kid. I remember playing Breakout it wasn't even on Atari. I didn't have an Atari because I was born in '86, which was just after the original Nintendo came out. But I remember Breakout from something, maybe it was on the computer, and it's always kind of connected with me. So when I saw that there was an environment available for it, I felt more interested in trying to learn how to beat that than I did Pong, which is another similar game that is also, kind of popular and used in the AI reinforcement learning space. So I think getting into the details of nitty-gritty of like what libraries I use and things like that is its own video topic on its own, just because of the depth that is there and the amount of different options you have available, along with the number of options. There's a sort of scale as to how well it's documented. So how easy is it for you to actually get started using it, and how well do their examples actually work? Without getting into the detail of what I actually did to set up the environment, because that's its own topic, and I kind of want to just talk about where I got so far. The library that I used is called Stable Baselines. Baselines is something produced by AI, OpenAI, and then Stable Baselines is a community sort of edition of it, where some people came together. They saw Stable Baselines is good from OpenAI, but it's not documented and it's not easy to use. So we're going to take it. We're going to try to marry it with sklearn and the ideas behind sklearn, which is a machine learning startup system, and try to take that code and the ideas behind there and marry it with Baseline. So that's how Stable Baselines was created. The amount of code required to actually just get up and started is just a couple lines of code, but in the details is where it gets complicated. Picking the different models, trying them out, seeing if you can alter the models and not alter the model, but alter the hyperparameters that go into how the system is going to train. All of those areas are that you kind of play around with, and Stable Baselines is a good library to get up and running there. I'll go into in another video some of the details around it, but I didn't want to get bogged down with that here. I just kind of wanted to show the results. So I did a number of different things when I was trying to get a breakout model to run. I tried a number of different libraries. Some of them were successful, some of them not. I really got stuck at kind of 3 points in the beginning. So I could only break about 3 bricks with my model at max, and then it would go back down and then go back up. The model would ping back and forth in terms of its performance, but I couldn't get it to break 3 points. What I ended up doing to actually get it to work was using a model called proximal policy optimization, and then the second version of it, so PPO2, which is what worked for me. And just taking the entire screen, I set it up so that it could run 16 games at once, and then iterated over that continually. I didn't actually take anything from the default hyperparameters. I just ran it a number of times. And that ended up getting me up to, I got some of my models were able to break about 400 points, which is really interesting. But I didn't get beyond that, and I think that's about the top score that you can achieve based on what people have done and published. I wasn't able to break any high scores yet, but that's something I want to get. I want to keep pushing. So one of the things I did to try to push through that barrier was instead of taking the entire screen and taking the entire spectrum of color available, so that you have red, green, and blue, and that would make I don't remember the number of colors that Atari supports, but you have a number of colors in the games that are possible. You can turn them into black and white as you pass them into your model, and you can also kind of cut the screen down a little bit because there's only a small playing space, and the rest is sort of it fills out. It has your reward printed out. It has your number of lives, things like that. And then you can also pass when the game loses. It was important. People wrote some papers on it. It was important to actually pass the losing screen and the losing reward in, and make sure the model doesn't cut that off. Or sorry, the code that you've written to build the model doesn't cut that off. And when I tried to do that, it hasn't actually worked out. So I must be doing something wrong. I haven't figured out why, my straight just run the game worked better than trying to use the method that was optimized in some papers and produced good results in some papers. So I haven't figured that part out yet. But that's the next stage, to try to figure out what I can actually alter to make the reinforcement learning algorithm perform better without reducing my performance, which is a back and forth game. It's not super straightforward what you need to do to get to the result. And as I said, about 400 points or so is the top performing that I've seen published so far, and there may be other papers that I haven't read, but that's what I know about. So one of the things you can do when you're training is get a look at what the video output is as it's training. You don't actually want to always be outputting the video, because the computer can actually play faster than you would have output on the screen. So it's usually 30 to 60 frames per second are the typical monitors. You can get some that are faster, but a game is usually played at, and I can't remember the max frame rate for Atari or what it used to be, but the game can play upward, the computer can play upwards of like 500 frames per second. So that's like over 500 actions that it selects per second instead of 30, so you can train a lot faster if you're not outputting the video and you're not consuming the CPU resources doing video output. So what I've done was take video at iteration points to see if how does the game improve over time. One of the things that you can kind of look at and see as this plays is the early on, it's not doing super well. It seems like a lot of as I said, there's 16 run at one time. A lot of them are somewhat random in terms of how it decides where it needs to move, and that's part of the learning algorithm. There's some randomness involved so that it doesn't get trained on something that works it doesn't develop a bias towards something that's not actually going to have long-term gains. You do some exploration first. But anyways, what is happening here is that some of them are going very random and completely missing the ball, but you can kind of tell that it's sort of developing a trend where it just moves it all the way to the right and then keeps it there, and it can hit one of the first bounces, and then some of them move all the way to the left then, and you kind of see some behavior developing. It's not scoring too well, but this is where you get for an average of about 2 or 3 points per running series of running games. All right, so now we're in about an hour's worth of training, and we can see that it's doing better. It's getting into the 20s and 30s in terms of the amount of points that it gets per game. You can see that it's somewhat developing. You can kind of see it trying to push through a specific area. It's not uniformly distributed. The breaks aren't uniformly distributed. And that could be random, or that could just be part of how the game is sort of playing. I don't think it's developed any strategy here other than just it's sort of figured out that the platform at the bottom should not miss the ball, and it's trying to orient the platform under the ball using left and right. So we can see it's getting better after about an hour's worth of training, but it's really not super impressive in terms of its performance. I mean, I think it's super neat that it's actually, it's a computer playing itself, which is funny to me. But it's not something that is going to be, a human player can play. Any human player can play about this well. And all right, here it is. Here's where I ended up, and this is the best performance I was able to get. You can see that one of the things it's figured out how to do is actually break through it's actually able to break through the line and get the ball up to the top where it starts bouncing, up and down, and then, getting a lot more points that way without having to actually risk more times that it hits the ball. And the ball actually starts to move quite a bit faster, as you get further on into the game. And I know that, it's not beating the best, human performance, because I think the total top score that you can get, you have about 2 levels, and then it just ends. The top score is somewhere in the 900s or so. Certainly not better than what a human player could do, but the average human player, I don't think, it would take a little while to get up to this point where we're able to hit the ball when it's moving, really quickly. And I don't know exactly how to get it to go and get higher performance. It's doing pretty well. I mean, you can see sometimes it digs through the center, sometimes it digs through the left, sometimes it digs through the right. There's different behaviors that it's built out depending on how the game is actually going. But I'm not exactly sure how to get this to work better. My guess is that it doesn't really understand that losing a ball is a problem. I just saw a score that was in the 400s, so like 420s, I think. But I'm not sure it's actually figured out that if you lose a life, that that's a really bad thing. So I'm not sure what I can do to improve on that. If it's just going to end up if you just run enough models, it figures out that the number is up there, and maybe it kind of figures out that in that state you need to worry or you need to do better or something like that. It seems like something that would be difficult it would take a long time to get there. But I'm pretty happy with the performance so far. I'm going to keep diving into it, see if I can get better performance, maybe work with a different game. But it's super interesting to watch for me, just to see a computer being able, just through iteration after iteration, and building a model that changes every time you do something correctly, and then every time you do something incorrectly, just reinforcing behavior based on just iteration through logic. I think that's super interesting. It's really, I'm always impressed as I watch it and as I see, it perform and create its own behaviors and things like that. So anyways, that's where I'm at with it for this week. I don't know exactly how long it's going to take me to produce something that I can showcase, next week or maybe the week after. But let me know if you have any questions. I'll do my best to answer them. As I said, I am still reading on this. I'm not an expert by any means. I'm not a researcher in it. I don't have a PhD in it. I didn't go to school for it. None of those things. I just picked it up, started reading, and this is where I am with it. I haven't done anything novel. If you're wondering what I've done, I've basically just implemented algorithms from someone else's work, and I've run them on a computer. I haven't really done anything very, pushing the envelope of what a computer can do. But this is just, something that I'm interested in getting into and sharing with other people. I think it's an interesting topic, an interesting field, and maybe as I go on, I have more ideas about what I want to do. Try to build I really want to get to a point where I could train a model to play Street Fighter against itself, in order to get a highly performing model to play an AI against or something like that. That would be really fun. It's going to take a while before I get there. I don't actually know how I'm going to be able to do that yet, or what algorithms and hyperparameters and things I'll have to do to mix in. Maybe one thing I can do here is I could, train it up to a certain point and then change something like the learning rate, things like that. As the model develops, that may produce a little bit higher performance. I really don't know how you could get it to perform to the level of actually beating the game and never actually losing a life. That's where I'd love to get. It may take a while. It may take a lot of reading to get there, but let me know what questions you have. I can provide resources. I'll need to do a separate video on how to set everything up because it's very specific. You have to get the right versions of things together, and there are probably multiple ways to do it, but the way I only know one specific way that's worked for me so far. If people are interested, or if you're just interested in seeing how this, what the models, how they perform and what it looks like when a computer tries to learn and play a new game. So let me know what questions you have. Leave them in the comments. I'll do my best to answer them, or at least direct you to the sources that I know about in order to increase your own level of knowledge and comfort in the area. But thanks for tuning in.